Dealing with unintentional grounding in ungrounded 480-volt systems requires a multifaceted approach. Firstly, system inspection and monitoring are paramount. Conduct regular electrical inspections to identify potential sources of unintentional grounding. Install voltage and current monitors to detect changes in system voltage and currents that may indicate a ground fault. Implement an arc flash hazard analysis to assess the risks associated with the ground fault and establish proper personal protective equipment and safety protocols. Secondly, grounding resistance monitoring is essential. Install a ground fault monitoring device that measures the resistance between the system conductors and ground. Set alarms to trigger when the resistance drops below a predetermined safe level, indicating a ground fault. Thirdly, proper equipment grounding is necessary. Ensure that all equipment connected to the system is properly grounded to a single-point grounding system. Inspect electrical panels and equipment regularly for loose connections, damaged insulation, or grounding issues. Fourthly, training and awareness are critical. Train personnel on the importance of maintaining an ungrounded system and the consequences of unintentional grounding. Establish procedures for handling and investigating any suspected or confirmed ground faults. Encourage employees to report any unusual electrical events or observations. Fifthly, fault investigation and correction are crucial. When a ground fault is suspected or confirmed, investigate promptly to identify the source. Isolate the affected area and remove the ground path to restore the ungrounded condition. Conduct thorough inspections and repairs to prevent the recurrence of ground faults. Sixthly, system coordination is important. Coordinate with the utility to ensure that the incoming power supply is properly grounded. If the utility's grounding practices change, assess the impact on the facility's ungrounded system and make necessary adjustments. Additional considerations include using shielded cables or conduit to minimize induced currents and reduce the risk of accidental grounding. Consider using surge protectors to suppress transient overvoltages that may cause ground faults. Install surge arresters at the point of connection with the utility to protect the system from lightning strikes. In more detail, let's explore the concept of ungrounded systems. An ungrounded electrical system is designed to operate without a direct connection to ground. This means that there is no intentional path for current to flow back to the source in the event of a ground fault. Instead, the system relies on insulation to prevent current from flowing to ground. The primary advantage of an ungrounded system is its ability to continue operating even with a single ground fault. When a ground fault occurs in an ungrounded system, the voltage of the faulted phase shifts towards ground, while the other two phases rise in voltage relative to ground. However, no significant current flows because there is no complete circuit. This allows operations to continue until the fault can be located and repaired, minimizing downtime. Despite the advantages, ungrounded systems present challenges. The first ground fault is not typically disruptive, but it raises the voltage to ground on the other two phases to the full line-to-line voltage. This can stress insulation and potentially lead to a second ground fault. If a second ground fault occurs on a different phase, a phase-to-phase fault can occur, resulting in a high fault current. This can cause equipment damage and pose a significant safety hazard. Additionally, locating the first ground fault in an ungrounded system can be difficult. Since there is no immediate interruption of power, the fault may go unnoticed for an extended period. Specialized equipment and techniques are required to identify the source of the ground fault. Now let's discuss system inspection and monitoring in more detail. Regular electrical inspections are crucial for identifying potential sources of unintentional grounding. These inspections should include visual examination of wiring, connections, and equipment for signs of damage, deterioration, or improper installation. Special attention should be paid to areas where moisture, vibration, or extreme temperatures may be present. Voltage and current monitors can be installed to continuously monitor the system for changes that may indicate a ground fault. These monitors can detect subtle variations in voltage and current that might not be immediately apparent. When a ground fault is detected, the monitors can trigger alarms or automatically shut down the affected equipment. An arc flash hazard analysis is essential for assessing the risks associated with a ground fault. This analysis involves calculating the potential arc flash incident energy at various locations in the electrical system. The results of the analysis are used to determine the appropriate personal protective equipment required for working on or near energized equipment. Next, let's delve into grounding resistance monitoring. A ground fault monitoring device measures the resistance between the system conductors and ground. This device provides a continuous indication of the insulation resistance of the system. When the resistance drops below a predetermined safe level, it indicates a ground fault. Alarms can be set to trigger when a ground fault is detected. These alarms can alert personnel to the presence of a ground fault, allowing them to take corrective action. In some cases, the alarms can also initiate automatic shutdown of the affected equipment. Moving on to equipment grounding. Proper equipment grounding is essential for preventing electrical shock hazards. All equipment connected to the system should be grounded to a single-point grounding system. This ensures that there is a low impedance path for fault current to flow back to the source. Electrical panels and equipment should be inspected regularly for loose connections, damaged insulation, or grounding issues. Any problems should be corrected immediately to prevent potential hazards. Regarding training and awareness, personnel should be trained on the importance of maintaining an ungrounded system. They should understand the consequences of unintentional grounding and the procedures for handling ground faults. Training should also cover the proper use of personal protective equipment and the importance of following safety protocols. Employees should be encouraged to report any unusual electrical events or observations. This can help identify potential problems before they escalate into serious hazards. When a ground fault is suspected or confirmed, prompt investigation is essential. The source of the ground fault should be identified as quickly as possible. This may involve using specialized equipment, such as ground fault locators, to trace the fault current. Once the source of the fault is identified, the affected area should be isolated. This may involve disconnecting equipment or opening circuit breakers. The ground path should be removed to restore the ungrounded condition. This may involve repairing damaged insulation or replacing faulty equipment. Thorough inspections and repairs should be conducted to prevent the recurrence of ground faults. This may involve tightening connections, replacing damaged wiring, or upgrading equipment. System coordination is also important. The facility should coordinate with the utility to ensure that the incoming power supply is properly grounded. This is essential for preventing ground faults from propagating from the utility system into the facility's system. If the utility's grounding practices change, the impact on the facilities and grounded system should be assessed. Necessary adjustments should be made to ensure that the system continues to operate safely and reliably. Shielded cables or conduit can be used to minimize induced currents. This can reduce the risk of accidental grounding. Surge protectors can be used to suppress transient overvoltages. This can help prevent ground faults caused by lightning strikes or other voltage surges. Surge arresters can be installed at the point of connection with the utility. This can protect the system from lightning strikes and other voltage surges that may originate from the utility system. Maintaining an ungrounded system requires careful attention to detail and a commitment to safety. By implementing the measures outlined above, industrial facilities can effectively deal with the challenges posed by unintentional grounding. This can help ensure a safe and reliable electrical distribution environment. Remember, even though the system is ungrounded, it is still crucial to ensure that all equipment is properly grounded for safety. This grounding is for personnel protection and should not be confused with intentionally grounding the system neutral, which is not done in ungrounded systems. The purpose of grounding equipment is to provide a low impedance path for fault current to flow back to the source, causing the overcurrent protection device to trip and energize the circuit in the event of a fault. This protects personnel from electrical shock hazards. In summary, dealing with unintentional grounding in ungrounded 480-volt systems requires a proactive and comprehensive approach. By implementing regular inspections, monitoring grounding resistance, ensuring proper equipment grounding, providing thorough training, conducting prompt fault investigations, coordinating with the utility, and utilizing surge protection measures, industrial facilities can effectively mitigate the risks associated with unintentional grounding and maintain a safe and reliable electrical distribution system. Furthermore, it is important to understand the specific requirements and recommendations of the variable frequency drive manufacturers. They often provide detailed instructions on how to properly ground or unground the drive based on the type of electrical system. Following these instructions is critical for ensuring the proper operation and protection of the drive. In addition to the measures mentioned earlier, it is also important to consider the impact of harmonics on ungrounded systems. Variable frequency drives and other nonlinear loads can generate harmonic currents that can circulate within the system. These harmonic currents can cause overheating of equipment, voltage distortion, and other problems. To mitigate the effects of harmonics, it may be necessary to install harmonic filters. Harmonic filters are designed to reduce the amplitude of specific harmonic frequencies, thereby improving the power quality of the system. Selecting the appropriate type and size of harmonic filter depends on the specific characteristics of the system and the harmonic currents that are present. Power quality monitoring can be used to identify the presence of harmonics and to evaluate the effectiveness of harmonic filters. This involves measuring the voltage and current waveforms at various locations in the system and analyzing the frequency content. The results of the power quality monitoring can be used to optimize the design and operation of the harmonic filters. Another important consideration is the use of isolation transformers. Isolation transformers can be used to isolate sensitive equipment from the rest of the electrical system. This can help protect the equipment from voltage surges, noise, and other disturbances. Isolation transformers can also be used to create separately derived systems which can be grounded or ungrounded as needed. The choice of whether to ground or unground a separately derived system depends on the specific application and the potential hazards. In some cases, grounding the system may be necessary to provide a low impedance path for fault current to flow back to the source. In other cases, ungrounding the system may be preferable to minimize the risk of ground faults. The decision should be made in consultation with a qualified electrical engineer. Finally, it is important to emphasize the importance of regular maintenance. Electrical equipment should be inspected and tested regularly to ensure that it is in good working condition. Connections should be tightened, insulation should be checked for damage, and overcurrent protection devices should be tested to verify that they are operating properly. Regular maintenance can help prevent problems before they occur and can extend the life of the equipment. In conclusion, dealing with unintentional grounding in ungrounded 480-volt systems requires a comprehensive approach that includes regular inspections, monitoring grounding resistance, ensuring proper equipment grounding, providing thorough training, conducting prompt fault investigations, coordinating with the utility, utilizing surge protection measures, addressing harmonics, considering isolation transformers, and performing regular maintenance. By implementing these measures, industrial facilities can effectively mitigate the risks associated with unintentional grounding and maintain a safe and reliable electrical distribution system.